useful research area. And you don't have to do anything, but it's necessary.
So, beta was at least not yet, but at least he begins to bring the active for some yeah. It's not that, it's something. So the next thing we're going to discuss will be canonical form of elements in small cancellation groups and the canonical triangle. So let me recall that previous time we have constructed small cancellation groups under certain conditions using the semi-canonical form, and actually each element may have finitely many different semi-canonical forms that all represent the same element. Now, it would be desirable, while not necessary to construction of the group, but once the group is constructed, we would like to see some unique presentation of each element as a certain word. And this would be given through the canonical form. Now, there are different ways to define this canonical form. This is one thing. And then, when it is defined, we will be interested to see what will be the canonical triangle. I mean, given two words and their product, we look on the canonical form of the first word, the canonical form of the second word, and the canonical form of their product. And then we will see that to a certain extent we're able to achieve some very strong conditions on the canonical triangle, but in a certain sense not more than we will be able to do. So let's start. The first I recall that we use certain parameters. So 0, 1, half, tau is a value of the threshold. Then we have taken lambda 0 and lambda 1 under a certain, but also, of course, the important thing is epsilon. This is the parameter that defines what are the equation for small pieces. Small pieces should not exceed the value epsilon. And then we assume that, for example, 1 is much bigger than lambda 0 in terms of epsilon, lambda 1 and tau. Lambda 0 is bigger than lambda 1, at least two epsilon, actually, and many epsilons, doesn't matter. This would be much bigger than half, and and tau will be bigger. Also set to epsilon. So all these things we consider. Now what we have considered the word in the lambda 1 semi-canonical form. And then we were able to take all of them inside the one layer map. So for an element we have a one layer map. one layer map is also depending on the constant lambda. We have taken to be depending on the constant lambda 1. So what does this mean? That we may have number of radius of this type, all of them should be in one layer, so we got one layer map. So what is our condition? That we assume that all the, so actually where we have this is a relator, this is a relator, all these cells on, we read the relators on the outer perimeter. Now and then we assume that this part is less, its measure is less or equal than lambda 1, and this is equal, and this for all of these edges that we see on the upper and the lower side of the one layer map subject to this condition lambda 1. Now, and then when we look on which are the, in a sense there is a unique maximal map with this property, such that all semi-canonical words representing the same element, they are passes in this one layer map, which may switch sides, but subject to the condition that the part that they take on each of these will be not bigger than lambda 1. I mean, if it switch sizes, so this and this and this together will be no bigger than lambda 1, the measure will be lambda 1, and for all of them. Now, then of course we would have the upper one, and the lower one also would be lambda 1 semi-canonical word, because we assume that all edges on the sides are subject to this condition, but there may be different other bases also, but not necessarily all of them, because it may be that if we switch the passes in the wrong way, then it will exceed this constant, because this will be close to the boundary, then we add to epsilon, we're above lambda 1. So on one hand, all lambda 1 semi-canonical words forms are represented by passes in this diagram, but there may be passes in this diagram that exceed this lambda 1 value. In any case, we have this map. Now, it means that to choose the canonical form will just mean to decide on which side of the every cell we have to take. Just some way, some uniform way to decide it. So let me first start to the simplest way to do it. The simplest way is we compare the words on the upper side and the lower side. Now, and then I have to assume that the group, that the relators are not proper squares. Assumption. For no relator R in Z R is equal to some square of an element. And by the way, when we will look on the Burnside problem, and then we will treat only the case of odd exponent. And here is precisely this situation where, in the case of even exponent that are ever related to the square of something, that the algorithm to choose a canonical form will break down. And then actually one needs some much more complicated arguments using the classification of finite two groups in this person group, as is done by Sergei Ivanov in his paper in Hijack. So, we just compare these elements and their inverses using first the comparison by length and then by the in the dictionary order that we input, we assume some order on the element on the generators and the inverses, and then we compare them lexicographically to the short lex order. Now, it may happen that this should be equal to this and the or to the inverse, and then we are at loss what part to choose. Then we will inspect these parts. So also maybe there is some kind of asymmetry that will help us to make a choice. But if the word is a proper square, then it may happen that this is precisely equal to this is precisely equal to this, and then we do not have a way to choose one side better than the other, the completely symmetric situation in this position. So unless this happens, we will be able to choose the shorter side. But if they are equal, we will just also inspect this side in order to define what is the best way. So in any case, we are making this shorter word, we're looking for each of them independently. Maybe this is here, this was this, etc. So this taking the shortest order is done independently for each cell. And then, which will be the canonical form? The canonical form will be exactly the one that goes to the correct side. In this case, it would be such a word. And then we obviously see what will be the R chart of this world, just its intersections with these cells. But I'm not claiming that the words appearing in the charts are the minimal ones, because one have different decisions on the side of it. So while this could be the minimal if the other side would be a certain position, but in the position that we actually take them, it may be not the minimal one. Because, you see, this was the best one. But, because we've taken this and this, so actually this may be shorter than this one. Because this adds to this, because we need to see this we see in the chart of it. So, but if we have a free hand to manipulate each of them, then this should be virtually the shortest one, and this for every of position in this chart. So this is the simplest way, intuitive, to take the canonical form. So
can you just repeat how you so to choose the side you
I'm looking on this on the two sides and comparing in them and their inverses in the short lex order.
Okay, so it has nothing to do with the measure.
No, it doesn't matter. Doesn't do the measure.
Okay.
Lexical order, that means
First, we look what is the shortest by the number of letters, and then what if they're equal, then taking a lexicographical ordering.
Okay.
So it doesn't matter, just some particular ordering that gives us definite result. And the short lex gives this distinguish between words if only they are not graphically equal.
But so it could be, for example, that this blue path is not lambda 1 semi-canonical. Could it be?
Oh yes, doesn't matter. It will be plus 2 epsilon.
Okay.
And okay. Or we could start with this lambda 1 minus 2 epsilon, and then all of them should be lambda 1. Okay. Now, what are the properties of this canonical form? First, one thing is obvious, that it is equivariant under taking inverses. The canonical form is equivariant under taking inverses. This is clear for the definition, because for the inverse word, we just inverse the one layer map. Just it would be the beginning. Here we have this and this just inverted. So this will be for that word. Now, when we take the way we choose sides, it is also equivariant, because we take the word and its inverse. So if this one was the preferred side here, then this will be the preferred side here. Because actually the lengths are the same. We compare this in the short lex order, so the inverse is the same lengths, and we take this word and its inverse, we compare, so we have actually the winners in this competition are just correspond to these two ones. So this will be the so it means that if we have chosen this side for this word, so we will have to choose this side for the inverse word, just by the definition of this competition that leads to the canonical form. Okay, this is easy, but it's an important property. We will see further that we strongly need this property in many situations.
So, but you're claiming that if you compare, so you have a word in its inverse, and then say V in its inverse, W in its inverse, and you compare them in the lexicographic order, and then it...
No, because trying to define what will be determined, what will the canonical form, I take this word and its inverse, this word and its inverse, and looking who is the smallest one.
Among the four?
Yes, among the four.
Okay.
And maybe if it is independent, so I have to add this also. I will actually have, well, now I will have 16 possibilities, and the winner out of 16 possibilities will be defined. But if we take the inverse, actually have the same set of words, because it is closed by taking inverses. So this is the way to assure that the result will be equivariant under taking inverses. Now, what will happen, for example, if we add just one letter to the word. How, or maybe more, but just one letter. How can this affect the normal, the canonical form? It turns out that there are some situations in which the result of just adding one letter will be very strong. And let me give an example how this can happen. Extra letter. Now, and it turns out that this will be the, for example, the one layer map for this word, where the measure here is precisely lambda 1. Now, next, this measure is precisely lambda 1. This is lambda 1. Oh no, this is too much for this. Assume at this point. Here is something less. So, this will be the one layer map for this word with one extra letter. If we're looking on the one layer map for this word without this extra letter, so it will happen the following. All of this we have at this point, and all this disappears. Why? Because when we have this is lambda, so if we would just hypothetically we could have all this, but when we take, so this is the same letter here, now and then it exceeds lambda 1, because this was precisely lambda 1, together it exceeds lambda 1. So we cannot take it inside this one layer map, because one layer map should not bigger than lambda 1. Now, so we have to remove this one. What happens now? This was precisely lambda 1. Now we have to add this part. It also exceeds lambda 1. We cannot take it. So we can continue indefinitely long until we meet something. This here it could be something just about 1/2 and about 1/2, for example. So it means that just adding one letter gives us one structure of the one layer left, but if we delete this letter, then because of our particular inequality that should satisfy in a very specific situation, all this self could not be but this is a kind of a domino. One falls, the other falls, etc. So we have this domino situation. And here we say something. Here, because it's much less than lambda 1, so even adding this, still it is much better than our restriction lambda 1. So this remains here. Now, it may be that when we have taken the choice of the canonical form, then, now, of course, in these cases, the choice, so we have to take a competition with this, because lambda 1 is much bigger than 1/2, so all of these will be much less than 1/2. So of course, these are the winners in both cases. So far, it does not affect the choice of the winner. Yes, these cells are present in the Valère diagram for this, they're absent here, but still we have the same winner, because this is much, lambda 1 is much longer than 1 minus lambda 1 plus or minus 2 epsilon.
But here, what if your measure is not the relative length?
I can just impose the situation, yes. I'm assuming that if this have a length that is close to this, so it will be also much shorter. So I do not need just to have the relative length, something that is connected with the relative length via certain inequalities. But definitely I require that something in this part is much better than this. Whatever. I can adjust otherwise the process of choosing in any case. So, but what we have further? Further could be the following thing. We can assume that here, both of them are close to 1/2. And the winner here was this one. It may happen, because we have to compare with this and with this. But when this cell is absent, we have the comparison is between this and this. And this addition may change the scales. So and then here the winner will be on this side. So it means that in the final result they will be on different sides. Now, what goes further, it will have the same winner from this point, etc. Because here we have, if this will be chosen, so this will be chosen, because it's the same comparison, whatever, the same outcome on all these sides to the end. So what finally happens, that the normal, the canonical form, here will go this way, going this way, and whatever are the local winners. On the other, here it goes the same way, but here it is a difference, a discrepancy, and then it continues go the same way here. So, in this example, we see that actually here is a real discrepancy between these canonical forms. And moreover, we do not have an estimate of this number of cells that is participating in this domino fold. But actually, we see that after this will be just the same result. And we will show that this is actually the situation in general. So, what I mean in general, it is an even more interesting situation when we look on the canonical triangle. So, we have three words.
You're saying that adding an edge will change the canonical form just by one cell?
Yes, But so let me say precisely. So assume we have three words. Then they will give us a thin triangle of the kind we have considered the previous time. Just composed of one layer matched with or without a central cell. It may or may not be here. So we have here some one layer map adding this, some maybe something here, whatever, and some here. Of course, there may be different configurations, how this go, how they meet the central cell, or they may be even not what I mean central cell, that its boundary have non-trivial intersection with each of the words, W1, W2, and their product. Then it could be also situations that do not have the central cell. So we have two cases. But for example, we do have a central cell. Now, and then of course we may have different situations with lambda 1. For example, we may assume that this one is less or equal lambda 1, then we will have the one layer map for this first and the third in this way, including this central cell. It may happen just. So, on the other hand, it may be that if we take this one, it will be bigger than lambda 1. So we cannot include this part of this. This will be shorter, so it will be included. Now, imagine that we have also here a similar domino situation. So I mean, this, so because we don't include this, this is too long. So I mean, this is precisely lambda 1, precisely lambda 1, precisely lambda 1, step 1/2 and 1/2. So what will be at? Here will also the same situation. This is lambda 1, lambda 1, 1/2, 1/2. What happens when we take the one layer made between two of these? This one will not be included because this is too long. Now then, this happens to be too long because it was lambda 1, but adding something, it exceeds the limit, so it falls the second until we have the situation. So actually, what will be the one layer made between two? Then it will be until this place, and then it will be only this, because this is this part is where the dominoes are falling. And it could be the same situation here. It goes here, so it could be only this. So, for this, without this side, and it will be without this side and over. And the similar situation for taking the first and the third. It may be this also may be too big. Here we have a domino situation at a certain place. Now, here, these are the short sides. So it will be going here, and we will still have, so it goes this way. This will have 1/2 and 1/2. So it goes until this place. It should go here because of the falling of the dominoes. It will be going here, and then should go, no, here it can go this way. Because, just a moment, yes, because this is a long shot, so it will be through this, for example. Because this is just lambda. Okay. So now what happens when we're trying to find the canonical form of each of them? So of course, when we have lambda, so the choose will be on the other side. Here will be on the other side. Here will be on the other side. Now, when we have half, then the choice may switch here, because if it, so we may have this or this included, or only included the canonical word, because here it is closed in half, and then if we do have this cell, or do not matters. So, for example, for this one, the choice will be this. For the same here, maybe here the choice when these are included. So the choice will be here, for this will be other. So in this case also, we have a discrepancy. So when we take the canonical form, it may be somewhere here. It will be going this, this way. And maybe here. And when we take this one, it will go the same here. And here will do another choice, because this cell is present, so it will go this way. Also here it should go this way until it meets this. And here also we may have H. So it means that no, here actually this is the same. It means here we may have the discrepancy in the middle cell. Now there may be some discrepancy on this side, some discrepancy on this side. In this example, there was no discrepancy on this, but actually it could be also the discrepancy on this side. Then it means that what we have here is that and now we have no control of how many dominoes are going here. It could be indefinite, but when it happens, there is just one region on each side that gives a discrepancy. After this, there will be no discrepancy for the following reason. In order that this switched side, so it should be very close to 1/2. Otherwise, adding or subtracting epsilon will do no difference. It means that then everything from this on will have exactly the same conditions for the competition for this one and for this one. I mean, this cell simultaneously gives us a discrepancy and just eliminates any discrepancy in the continuation of it. Therefore, there will be no more than one cell. And the same on the other side, the same reason of all of these three branches, and of course the middle cell, if it exists, could be this way in each of them, so it is here is not completely natural that maybe a discrepancy, because this will go this way, this will go this way, and this way, so we have discrepancy in the middle. In any case, we have no more than 4 points of discrepancy. It means that when later I will show, this was an example, later I will show proving the full generality. This is what happens. But what is the meaning of it? That if we take these canonical forms of the element, it means we have our group G. and we have a mapping from the group to the three groups. Certainly it is not homomorphism, but it's just a mapping, choosing of the canonical representatives. Now, and then if we consider the corresponding recital, I mean representative of W1 times representative of W2 times representative of W2 minus 1, W1 minus 1, then it will be equal to a product of most four conjugates. I mean, taking some relator on one conjugated by some word V1, R2 conjugated by V3, R3 conjugated by V3, and R4 conjugated by V4, which I mean RV is V minus 1 RV. So because when we have this, we consider that this is a conjugated of relator times conjugated of another relator times conjugated of a third relator times of third relator. So we have this will give us a course cycle with the property that is inside very specific set. The product of at most four conjugates to the relators. Finished at the moment? So, now, of course, one can prove that if there is a canonical form, that automatically this is a small cancellation group with relations. Now, here is the following question. Given more general classes of groups, now for groups with iterated small cancellation, we will be able to show that a similar thing happens, but here's a number of these conjugates will be depend on the group, but it will be bounded by the group only, irrespective of these W's. Now, the similar question is it possible to choose such canonical representative for a, say, arbitrary hyperbolic group without two torsion? Actually, in a work with Slil many years ago, we very much would like to have this. Instead, we have something weaker, that we had just a bounded number of canonical forms, that at least one of them had this property, and we could not predict in advance which one will have this property. Now, if we're trying one singular canonical form for hyperbolic groups without two torsion, that will be a bounded number of conjugates, this is still open, and of course, we would like to somebody who solve it. Okay, I make the, now this is the end of this. Now make us a break. There is a lot of results about hyperbolic groups, but they may be used for it. So far,